Welcome to Lecture 7. This week we're going to finish our discussion of probability. We'll cover Chapter 20, Concepts of Probability, Chapter 21, Conditional Probability, and Chapter 22, Probability Trees. First, let's talk about some concepts of probability. Before we do that, let me remind you about union and intersection. The union of two sets A and B, or for us it's going to be the union of two events, is going to be everything in A together with everything in B. The intersection of two sets A and B, or for probability it would be two events A and B, will be the things which are in both A and B. For example, let's suppose we have one die. We're going to roll this. This die has the numbers 1, 2, 3, 4, 5, 6 on it. So the sample space is the set containing the numbers 1, 2, 3, 4, 5, and 6. We're going to assume that each of these simple events is equally likely. So the probability of getting each number is going to be 1 divided by 6. Two questions. Question number 1. What is the probability of rolling a number which is even and greater than 3? What is the probability of rolling a number which is even or greater than 3? For and, we're going to be using intersections. For or, we're going to be using unions. We need two compound events. Let A be the even numbers in S, that's 2, 4, and 6, and we're going to let B be the numbers greater than 3. So that's the set containing 4, 5, and 6. What is the probability of getting an even number and a number greater than 3? We want the intersection between A and B. The numbers which are even and greater than 3 are 4 and 6. So the probability of this, the probability of A intersection B, is 2 divided by 6. 2 because there's two numbers in A intersection B, and 6 because in total the die has 6 sides. For or, we use unions. We want to have an even number or a number which is greater than 3. So we're going to be doing A union B. The numbers which are either even or greater than 3 are 2, 4, 5, and 6. 6, for example, is both even and greater than 3. This set contains 4 elements and the sample space contains 6. So the probability of A intersection B is 4 divided by 6. Now, last week we had the addition principle for counting the number of objects in a set. The number of elements in A union B is the number of elements in A plus the number of elements in B, but so that we don't count the same elements twice, we do minus the number of elements in A intersection B. We have the same formula for probability. The probability of A union B is the probability of A plus the probability of B minus the probability of A intersection B. So, for example, you roll 2 dice, and these dice are the same. We can assume that these are fair dice, so each side is equally likely to finish on top. And these dice have the numbers 1, 2, 3, 4, 5, and 6 on, so ordinary dice. What is the probability that the sum is either 5 or 10? And then question 2, what is the probability that either the sum is greater than 9 or both dice show the same number? And we're happy with, for for example, 5 and 5, because that's showing the same number and greater than 9. We're happy with that. So question 1, first of all, how can we get a 5 or a 10? We're going to let A be the compound event that the sum is equal to 5. We could have 1 and 4, 2 and 3, 3 and 2, or 4 and 1. And then we're going to let B be the compound event that the sum is equal to 10. So that's 4 and 6, 5 and 5, or 6 and 4. You will note that the intersection of these two compound events is the empty set, because we can't have a sum is 5 and a sum is 10 at the same time. So because the probability of A intersection B is 0, all we need to do is probability of A plus the probability of B. So how many elements are in the sample space? 6 on the first die, 6 on the second die, 6 multiplied by 6 is 36. There's 4 elements in A, so 4 over 36, and there's 3 elements in B, so that's 3 over 36, or 7 over 36 in total. How can we get greater than 9 or the same number? We need 2 compound events. Let's call these C and D. C is going to be the sum is greater than 9. That's how we do it. And D is going to be both dice show the same number. 1, 1, 2, 2, 3, 3, etc. Each one of these compound events contains 6 elements. But these are not distinct events because there are some simple events in both compound events. 5 and 5 is in both C and D. 6 and 6 is in both C and D. C intersection D contains 2 elements. So we use our formula. The probability of C union D is the probability of C plus the probability of D minus the probability of C intersection D. So that's 6 over 36 plus 6 over 36 minus 2 over 36. And that's 10 over 36, or we simplify it as much as we can to 5 over 18. Next, I want to talk about complements. We remind you, a complement is everything that's in this case, the sample space, but is not in the event A. And that's useful for us because the probability of event E is equal to 1 minus the probability of E complement. Sometimes it's going to be easier to calculate 1 minus the probability of EC than to calculate PE directly. So, for example, a box contains 45 whiteboard markers, is delivered to Istanbul Okan University. 9 of these markers are red and the other 36 markers are black. Your teacher is given 10 markers at random. He will be happy if 1 or more of his markers is red. What is the probability that your teacher will be happy? In other words, what is the probability that at least one of these 10 markers is a red marker? So let E be the compound event that one or more of the markers is red. We want to calculate the probability of E. But it's actually going to be easier to calculate the probability of E complement. That's the event that all 10 markers are black. We're told that the markers are given randomly. So that means each simple event is equally likely. So to calculate the probability of E complement, we're just going to do the number of elements in E complement divided by the number of elements in the sample space. How can we be given 10 black markers? Well, remember, in total there's 45 markers, but 9 of them are red, so that means 36 of them are black. The number of ways of choosing 10 from 36 is 36C10. The number of elements in the sample space, remember there's 45 markers, and we want to choose 10 of them. How many ways are there of choosing 10 from 45? 45 choose 10. So using the theorem, the probability that we want, P of E, is 1 minus the probability of E complement. So that's 1 minus 36 choose 10 divided by 45 choose 10. And then using your calculator, we can calculate that that's approximately 0.92. Another example. In a class of 30 students, what is the probability that at least 2 students have the same birthday? Now, for birthday, I mean month and day. I'm not interested in them being born in the same year. And to make our calculation a little bit easier, we're going to ignore the existence of the 29th of February. So we're going to be assuming that there are 365 days in a year, and we're also going to assume that each day is equally likely. So that means the first student can be born on any of 365 days, and then the second student can be born on any of 365 days, so 365 times 365. And then for the third student could be born on any of the 365 days, so 365 multiplied by 365 multiplied by 365 for 3 students, and then go on. We have 30 students, so it's going to be 365 to the power 30. We want to calculate the probability that 2 or more people have the same birthday. But it's going to be easier to calculate the complement of this. We're going to calculate the probability that all 30 students have different birthdays, and then we're going to do 1 minus this probability. So first thing to do is to calculate the number of elements in E complement. How can we have 30 students having different birthdays? Well, the first student could have any of 365 birthdays. For the second student has a different birthday. So the second student could have any of 364 birthdays. And then when we come to the third student does not have the same birthday as the first student and does not have the same birthday as the second student. So the third student could have any of 363 birthdays, and so on. Because we have 30 students, the last one is going to be 336. That's 365 minus 29. That's the same as 365 factorial divided by 336 35 factorial, which is the same as 365 p30. So the probability that all 30 students have different birthdays is the number of elements in each complement divided by the number of elements in the sample space. But that's not the probability that we want. We want the probability that 2 or more students have the same birthday. So we're going to do 1 minus the probability of E complement. And when we get our calculator out and we calculate this, it's approximately 0.706. That means if we have a class of 30 students, the probability that 2 or more students have the same birthday is approximately 0.706, or approximately 70.6%. Our second topic for this week's lesson is conditional probability. The idea here is that sometimes the probability of an event will depend on another event. For example, if A is Ali has cancer and B, Ali is a smoker, then clearly the probability that A occurs will depend on B. These are not independent events, that one will depend on another. For this, we have the idea of conditional probability. The probability of A, line B, is the probability of A if we already know that B occurs. This is called the conditional probability of A given B. So let me say that again. A is the event that we want to calculate the probability of. B, we already know occurs. And we have a nice formula for calculating this. The probability of A given B is the probability that A and B both occur, so probability of A intersection B, divided by the probability that B occurs. For example, a bag contains red and blue marbles. 2 marbles are drawn without replacement. The probability of selecting a red marble and then a blue marble is 0.28. The probability of selecting a red marble on the first draw is 0.5. What is the probability of selecting a blue marble on the second draw if we already know that the first marble was red? So we're going to be doing conditional probability. R is going to be the event that the first marble is red, and B is going to be the event that the second marble is blue. We know that the first marble is red, and we're asked to calculate the probability that the second marble is blue. So we're doing probability of B over B intersection R divided by the probability of R. And we're told these. The probability of getting red, then blue, is 0.28, and the probability that the first marble is 0.5. So that means the answer to this question is 0.56. Your friend says that when she rolled a die, she rolled an odd number. What is the probability that your friend rolled a 3? We can answer this with conditional probability. Let A be your friend rolled a 3. We want to calculate the probability of A. Let B be your friend rolled an odd number. We already know that B occurred because Your friend told us that. The probability of rolling a 3 is 1 over 6. The probability of rolling a 3 and rolling an odd number, well, 3 is odd, so that's just the same as probability of A. The probability of rolling an odd number is a half, because 3 of the numbers are odd and 3 of them are even. So we put these numbers into our formula. We want to calculate the probability of A given B, the probability that your friend rolled a 3, given that we already know that she rolled an odd number. So it's probability of A intersection B divided by probability of B. 1 over 6 divided by a half, or 1/3. And that makes sense, because we could answer this question another way. If we know that she rolled an odd number, then we know either she rolled 1, 3, or 5. There's 3 numbers that she could have chosen, so 1 in 3. Okay, now, given this formula we've been using, probability of A intersection, probability of A given B is the probability of A intersection B divided by the probability of B. Multiply both sides by the probability of B. We have the formula that the probability of A intersection B is the probability of B multiplied by the probability of A given B. But remember, A intersection B is just the same as B intersection A. And using this formula, but just swapping the positions of A and B, we get probability of A multiplied by probability of B given A. So that means these two things must be equal. Probability of B multiplied by probability of A given B must be the same as probability of A multiplied by probability of B given A. Let's write that as a theorem. As we've just seen, the probability of A intersection B is the same as probability of A multiplied by probability of B given A, which is the same as probability of B multiplied by probability of A given B. Or rearrange it again. Probability of A given B is the same as probability of A, probability of B given A divided by probability of B. My next idea is called the Monty Hall problem. Suppose that you're on a TV game show, and let's suppose you're given the choice of 3 doors. Behind one door is a car, and behind the other are goats. So you're going to choose a door, and you're going to get a prize behind the door. So let's say you pick a door. Let's say you choose number 1, and the host of this TV game show, who knows what's behind each door, he opens another door. Let's suppose he opens door number 3, and he shows you that door number 3 has a goat behind it. And then he says to you, instead of door number 1, do you want to pick door number 2? Should you stick with door number 1, or should you change your mind and have door number 2 instead? Is it to your advantage to change your mind and switch to door number 2, or is it to your advantage to stay with door number 1? This problem is named after an American TV game show host called Monty Hall. And this is a problem which seems to confuse a lot of people that haven't studied probability. So let's think about this. We know that there's one car, and we know that there are 2 goats, but we don't know where the car is. The car might be behind door number 1, the car might be behind door number 2, or the car might be behind door number 3. We don't know where it is. You're going to choose a door. What is the probability that the car is behind the door that you choose? Well, that's easy, right? The probability that the car is behind the door that you choose is 1 over 3, because it's 1 car and 3 doors. That's correct. And then what happens is the host opens another door and he shows you that there's a goat behind the other door. So that means now there's 2 closed doors. Behind one of these doors is a car, and behind the other one is a goat. What is the probability that the car is behind the door that you chose? So there's 2 closed doors. One of them has a car, one of them has a goat. So the probability that the car is behind the door that you chose is 1 over 2, right? No, that's wrong. Why is that wrong? Let me explain. To understand this, let's look at all of the possible outcomes if you choose door number 1 first. All the doors are equal, so it doesn't really matter which door you choose. The probabilities are going to be the same. So let's just suppose that, first of all, you choose door number 1. There might be a car behind door number 1 and then goats behind door 2 and door 3. And let's say the host, who knows where the car is, opens door number 3 and he shows you that there's a goat behind door number 3. So now you have a choice. You can stay with door number 1, or you can change your mind and have door number 2. If you keep with door number 1, then you win the car. But if you change your mind and you say you'll have door number 2 instead, then you lose. What's the next possibility? The next possibility is that the car is behind door number 2. So again, first you choose door number 1. Then the host opens door number 3 and he shows you that there's a goat behind door number 3. Then you have the choice. You can stay with door number 1, or you can change your mind and have door number 2 instead. If you stay with door number 1, then you lose. If you change your mind and you have door number 2 instead, then you win. And the third possibility is that the car is behind door number 3. First, you choose door number 1. The host opens door number 2 this time, and he shows you there's a goat behind door number 2. And then the host asks you, do you want to stay with door number 1, or do you want to change your mind and have door number 3? If you stay with door number 1, then you lose. If you change your mind and have door number 3 instead, then you win. So look at these columns. If you don't change your mind, you're going to win 1 in 3. But if you do change your mind, then you're going to win 2 in 3. So we can see from this table that if you don't change your mind, then you have a 1 in 3 chance of winning the car. But if you do switch, if you do change your mind and have the other door, then you have a 2 in 3 chance of winning the car. As I said before, these are the probabilities if you choose door number 1 first, but all doors are identical, so it doesn't matter which door you choose first. The probabilities are going to be the same if you choose door 2 or door 3 first. Let's think about this another way. Again, let's suppose that to start with, you choose door number 1. So at the start, the chance that the car is behind door number 1 is 1 in 3, and the chance that it's behind either door 2 or 3 is 2 in 3. Let's change the problem a little bit. Let's imagine that the host doesn't open the door. He just says, you can change your choice for both of the other 2 doors. So you could either have door number 1, or you could have both door number 2 and door number 3. So would you switch then? Would you swap door number 1 for door 2 and door number 3? Now remember, we know at least one of doors 2 and 3 hides a goat. And remember, the host knows where the car is. The host doesn't open a door at random. He always opens a door with a goat. So when the host opens a door, he isn't giving you any extra information. We already know that one of these 2 doors has a goat. So that means the probabilities don't change. They don't change to a half and a half. They stay with 1/3 and 2/3 because we don't get any extra information when the host opens a door. Let's answer this question again. Let's answer this using conditional probabilities. Let C be the event that door number 1 has a car behind it, and let C complement be the event that door number 1 does not have a car behind it. So in other words, C complement is going to be the event that door number 1 has a goat behind it. And E is going to be the event that the host opens a door with a goat behind it. What are the probabilities of these events? Well, the probability that the car is behind door number 1 is 1/3. So the probability there's a goat behind door number 1 must be 2/3. If there's a car behind door number 1, what is the probability that the host opens a door with a goat behind it? The probability is 1 because the host always opens a door with a goat behind it. And if there is a goat behind door number 1, what is the probability that the host opens a door with a goat behind it? Again, it's 1. The host always opens a door with a goat. Now that we have these numbers, we can put these into our formula. What is the probability that the car is behind door number 1, given that the host has opened a door with a goat behind it? Using our theorem, that's the same as PC, PE, given C divided by PE. Now on the bottom, PE is the same as PE intersection C plus PE intersection C complement, and then using an idea from before, using the theorem, that's the same as PC given PE given C plus PE complement, PE given C complement. Now that we have this, we can put the numbers in. PC was 1/3. PE given C is 1. Same on the bottom. PC complement was 2/3, and PE given C complement was 1. And when we calculate this, the probability is 1/3. So that means it doesn't matter if the host opens a door or not. The probability that the car is behind door number 1 is always 1/3. So the conclusion from this that we've answered this question 3 different ways. The conclusion is, if you go on a TV game show and if you're playing the Monty Hall problem, you should always switch door if you want to increase your chance of winning the car. And that brings us to our final chapter of this week's lesson. We're going to talk about probability trees. First example is about 5 balls in a box. The box contains 3 red balls and 2 yellow balls. 2 balls are randomly taken out of the box without replacement. What is the probability that the second ball is yellow? To answer a question like this, we can draw a probability tree. I'm going to start just here where it says start, and then I'm going to look at the possibilities for the first ball. The first ball can either be yellow or red. What are the probabilities of these? Well, there's 2 yellow balls out of 5, so the probability that the first ball is yellow is 2 over 5, and the probability that the first ball is red is 3 over 5. And then we move on to the second ball. Again, for the second ball, there's 2 possibilities, either yellow or red. Let's look at the top part of the tree first of all. First ball we've taken out is yellow, so that's gone. That means there's 4 balls left. One of these 4 balls is yellow and the other 3 are red. So the probabilities are going to be 1 over 4 and 3 over 4. And then we move to the second ball, so the second half of the tree. First one we've taken out is red, so that's gone, that's not there anymore. And then we have 2 yellow balls out of 4 and 2 red balls out of 4. So the probabilities here are going to be 2 over 4 and 2 over 4. Along each of the branches of this tree, we can multiply the probabilities together. So up here, 2 over 5 multiplied by 1 over 4 is 1 over 10. And then to get to this yellow, 3 over 5 multiplied by 2 over 4, which is 3 over 10. If we add these together, we get the probability that the second ball is yellow. Probability of yellow plus probability of red yellow is 1 over 10 plus 3 over 10, or 2 over 5. So the probability that the second ball is yellow is 2 over 5. But of course it is. We have 5 balls and 2 of them are yellow, so of course the probability that any particular ball is yellow is going to be 2 over 5. Another example, Boris and Kia are playing tennis. The first player to win 2 sets wins the match. In each set, the probability that Kia wins that set is 2 over 3. Find the probability that Boris wins the match. Find the probability that 3 sets are played. And find the probability that the player that wins the first set wins the match. The first thing to do is to draw a probability tree. We have 3 sets, and in each set, either Kia wins or Boris wins. And in each set, the probability that Kia wins is 2 over 3, and the probability that Boris wins is 1 over 3. Now, in tennis, if we're playing best of 3 sets, as soon as one player wins 2 sets, the match finishes. So if Kia wins the first 2 sets, that's the end of the game, and it's the end of the match. And if Boris wins the first set and the second set, then again, that's the end of the match. We stop just here. Along each of the branches, we multiply the probability. So for the probability of doing KBB, for example, K, then B, and then B, 2 over 3 multiplied by 1 over 3 multiplied by 1 over 3, which is 2 over 27. Now we can answer the questions. What is the probability that Boris wins? So, looking at all of the possibilities that Boris wins 2 sets. It could be KBB, or BKB, or BB. That's the probability. That's the possible cases where we have 2 Bs. Add these together: 2 over 27 plus 2 over 27 plus 1 over 9, or 7 over 27. Question 2, what is the probability that 3 sets are played? To get 3 sets played, we could have KBK or KBB, BKK or BKB. Add these probabilities together, we get 4 divided by 9. What is the probability that the player who wins the first set also wins the match? That could occur if we have KK or KBK or BKB or BB. Add these 4 probabilities together, we get 7 over 9. Let's do another example. This time we're given this probability tree and we're asked to calculate the probability of B. Well, where's B? There's 1 here, 1 here, 1 here, and 1 here. We need to calculate the probability of each of these 4 branches, and then we need to add them together. So that's the probability of RMB plus the probability of RNB plus the probability of SOB plus the probability of SB. Add these all together, and I'm going to leave this for you to check. I'm being deliberately fast here. Please check my calculation, and please check that this is 79 divided by 100. And then one more example, final example of today's lesson. Ron Weasley has a bag with 7 blue sweets and 3 red sweets in it. He takes a sweet at random from the bag and then puts it back in the bag. Then he picks a sweet at random from the bag and he eats it. Finally, he picks a 3rd sweet at random. Draw a probability tree to represent this situation. So, we have 10 sweets, 7 of them blue and 3 of them are red. So to start with, the probabilities are going to be 7 over 10 and 3 over 10. First, Ron takes a sweet from the bag and then he puts it back in the bag. So 7 over 10 and 3 over 10 are our probabilities. Step 2, he takes another sweet from the bag. Again, there's 10 sweets in total, so 7 over 10 and 3 over 10. But then he eats this 2nd sweet. So now there's only 9 sweets in the bag. And then he picks a 3rd sweet at random. So let's draw our probability tree. First, the first sweet could either be blue or red. And as I said, we have 10 sweets, so the probabilities are 7 over 10 and 3 over 10. And then he puts the sweet back in the bag, and then he shuffles it all around, and then he picks a sweet at random. So again, the probabilities are going to be 7 over 10 and 3 over 10. But this time he eats that sweet. So now there's only 9 sweets left in the bag. If he eats a blue sweet, that means there's 3 red sweets and there's only 6 blue sweets left. So the probabilities are going to be 6 over 9 and 3 over 9. But if he eats a red sweet, there's still 7 blue sweets, but now there's only 2 red sweets left. So the probabilities are going to be 7 over 9 and 2 over 9. And then the bottom half is going to be the same as the top half. And that is the end of this week's lesson. Next week, there's no lesson because you have your midterm exam starting at 9 o'clock. 2 weeks from now, we also do not have a lesson because you may or may not have an exam for another course. So our next class will be in 3 weeks' time. Are there any questions?